For billions of years, galaxies form stars out of molecular gas, and at the end of their lifetime, those stars return that gas back to the gas reservoir from which they were formed. However, when we look out into the local universe, we see that roughly half the galaxies are no longer able to form stars. Therefore, the cycle of forming stars from molecular gas and returning that gas back to the reservoir that made them must inevitably be broken. Understanding the mechanisms that drive that change requires both observations of molecular gas and of the stars and star formation rate. Previous surveys combining both molecular gas and stellar observations have been limited to either large but unresolved surveys such as X-cold gas, or small but high-resolution surveys such as FANGS. The work I'll present today strikes a balance between these two previous regimes without taking any data or requiring any new observations from the world's best telescopes. If you're interested, stick around and let's talk about the details. The optical data I use in this work comes from the Sloan Digital Sky Survey, which is really a survey of two parts: a global photometry survey and a spectroscopic fiber survey, where every fiber is 3 arcseconds in diameter placed on the center of every galaxy. This 2-in-1 survey style gives us two independent measurements of the star formation rate and stellar mass of every galaxy in the survey, though they're on slightly different spatial scales. The fiber spectroscopy only comes from the central 1 or 2 kiloparsecs, while the global photometry is the entire galaxy. By using both of these measurements, we can kind of get what I call a semi-resolved perspective, where we have the inner region defined by the fiber and the outer region defined by the light of the global photometry minus the fiber. The millimeter data necessary to measure the molecular gas masses of these galaxies comes from the Atacama Large Millimeter Array, otherwise known as ALMA. ALMA is an assembly of 43 different radio antennas located in the Chilean Atacama Desert. Each of the 43 different antennas can work together as one telescope, but can be independently moved to change the resolution and sensitivity requirements of the observation. The typical process for conducting observations on a telescope like ALMA requires you to submit a proposal which, if accepted, will be observed the following year. However, the rate of accepted proposals is on the order of 10%, which means even if you have a really good science idea, it's unlikely that you'll get time on the telescope. Although every observation conducted by ALMA, after a 1 or 2 year proprietary period for the PI to work with that data, is added to the ALMA Science Archive where it is publicly available. The ALMA Science Archive has thousands of world-class observations in it that have been used maybe once or twice for a specific project and then are no longer being used. While many previous works have used the ALMA Science Archive to add targets to their sample or to conduct entire projects, no one has undergone the technical challenge of assembling all the galaxies into one coherent dataset. In this work, I took galaxies from the Sloan Digital Sky Survey and looked for observations of those same galaxies in the ALMA Science Archive. After requiring a few additional cuts, such as a resolution smaller than the SDSS fiber and a maximum resolvable scale larger than the optical size, I find about 298 galaxies. I took those 298 galaxies and downloaded their raw data onto the CAMPHAR Science platform, where I calibrated them either using the default calibration scripts that are provided with the data, using the Science Ready Data Product Service available online, or by contacting the help desk for observations of early cycles. Combining the data from the 43 different ALMA antennas into one coherent image and a molecular gas mass is no easy task. For this, I used the thoroughly tested and reproducible pipeline developed by the FANGS ALMA team, with a few minor tweaks. After a few quality assurance checks of my own, the final sample is 277 galaxies for which we have a semi-resolved perspective of inner and outer molecular gas masses, star formation rates, and stellar masses. I call this dataset the SDSS-ALMA Legacy Value Archival Gas Exploration, or SALVAGE. With this dataset, we can approach global scaling relations with large sample statistics and a new, higher resolution perspective than ever before. Let's get into it. Here's 25 galaxies from SALVAGE, with representations of their optical data on the left and their millimeter data on the right. The optical data traces the stars and the star formation rate. On the right-hand side, the millimeter data traces the location of molecular gas, which is the fuel for star formation. As we go from vigorously star forming in the top left to not so star forming in the bottom right, you see that the morphology of the molecular gas maps changes. The star forming galaxies tend to be more concentrated and less disturbed, while the less star forming galaxies may have holes in their molecular gas mass or show signs of disturbance. Here's the first science plot that comes in the paper. In the top panel, we show just the star forming main sequence for galaxies that are detected in molecular gas. The gray shading in the background is the X-cold gas survey, which was a larger but unresolved survey of the past. And you can see that galaxies tend to form a star-forming main sequence where their star formation rate scales with their stellar mass. However, SALVAGE now provides a perspective where we can look within those galaxies to see where the star formation is occurring. And you can start to see the beginnings of a trend where vertically your distance from the star forming main sequence changes color on the scale bar here, which is the ratio of the inner specific star formation rate to the outer star formation rate. So galaxies above the main sequence tend to have centrally enhanced star formation, while galaxies that are falling below the main sequence tend to have less star formation in their central regions. So the position of the location of star formation within your galaxy is driving its position on this global star forming main sequence. However, when you look at the same thing in the molecular gas main sequence, which is the relationship between molecular gas and stellar mass, you see no such trend. Galaxies on the main sequence, above and below the main sequence, have gas fractions that are enhanced in the middle, deficient in the middle, and all over the place. And in short, my takeaway from this is that the location of your molecular gas mass has no bearing on its position of the molecular gas main sequence, the global molecular gas main sequence. In the next plot, we unpack what I think is the more interesting result, which is that the star formation rate deviates in the inner and outer region depending on where you are relative to the global star forming main sequence. Does that also change the properties of the molecular gas and star formation efficiencies? So for example, in the middle panel here, we see that for galaxies where their star formation rate is below the main sequence, so that is negative on the x-axis, or in this kind of green regime, the inner regions, which are the red dots, have less gas than the outer regions. And the flip side is true for galaxies above the main sequence. Galaxies above the main sequence have enhanced central molecular gas. And I take this to say that the central gas is driving a galaxy's position above or below the main sequence. Meanwhile, on the main sequence, you see on the right-hand panel that the biggest change is in star formation efficiency. This is what changes the galaxy's star formation for galaxies on the main sequence. Whether the top or the bottom of the main sequence depends on your star formation efficiency in the central region. Lastly, to explore what might be driving galaxies to change their global star forming status, to have lots of star formation or no star formation going on at all. I tried testing a few different gas metrics and to see which one correlates best with its global star formation rate change. In panel A, we show the global gas reservoir and how that relates to the global star formation rate change. In panel B, we show just the central gas fraction. In panel C, it's just the outer gas fraction. And panel D is the ratio between the inner and the outer. And looking at panel B, we see that it has both the highest correlation coefficient and the lowest intrinsic scatter, meaning that global star formation rate status, or change, is driven mostly by the availability of gas in the central region, even more so than the global gas reservoir, as in panel A. With data that already existed elsewhere, from the Sloan Digital Sky Survey and in the ALMA Science Archive, I've brought them together to produce something that I think is both useful for its own science and as a tool for the community. In this work, we used it to show something that I think is really cool, that the central region of galaxies are particularly exciting and important and have large ramifications for global change to the star formation rates. This might be due to galaxy mergers causing inflows of gas, causing starbursts that then provide feedback and remove the gas or de-excite it, and so on. Or even AGN removing gas from the central regions, which is something that I will explore in the next paper in this series. This paper taught me a lot about radio interferometry and different computing platforms, and I can't thank the experts enough that helped me along the way. And if you're interested in reading more about this, please go check out the paper. For now, thanks for watching.